So now we're going to start the third part of chapter 4. And this is going to be a conformational analysis of butane. Remember, I did this for you in the video using the molecular models. And I showed you the actual rotation about the carbon single bond between C2 and C3. And so go back and look at that part, play that back, and watch it now that we're about to discuss it here, because you really need both parts. That was not a complete discussion. That was just a demonstration of how to use your models and how to look at them. So here we're looking at the rotation of butane about the carbon bond between C2 and C3. And in the Newman projection here, we're looking down the carbon bond between C2 and C3. And you can see here the two methyls in this staggered conformation are as far apart as possible. Then you rotate by 60 degrees. Now you have, this is supposed to be the eclipsed conformation, where this methyl is eclipsing the hydrogen in back, and this hydrogen in front is eclipsing the methyl in back. And so you're going to have interactions between the hydrogen and methyl, the hydrogen and methyl. And remember, we just finished calculating that those are worth 6 each, 6, 6, and 4. So if you add up 6, 6, and 4, what do you get? You get 16. So here it is. This is the energy barrier to going from this, rotating from this staggered conformation to that staggered conformation. And notice that this staggered conformation, the one that is, this is called gauche. This one is a little bit higher in energy than that one. It's 3.8 kilojoules per mole higher, because the two methyls are next to each other and will interact somewhat sterically. Here they're pointed in opposite directions. There's going to be no interaction between them. Now we move on and we go uphill again. Now we have the two methyls in this eclipsed interaction, this eclipsed conformation. You're going to have the two methyls as close together as possible. And so remember, these are worth 4, 4, and so this is going to be worth 11. So 4, 4, that's 8. From 19, this is going to be worth 11. And then I'm not going to discuss moving on forward because this is symmetrical. These are the same as those, and there's no point in discussing these also. So for the sake of time, I'm going to move on. The stability of the different staggered conformations differs by 3.8. And so here these methyls are said to be anti to each other because they're pointed in opposite directions. They're farthest apart. And this one, notice its spelling, this is called gauche because they are next to each other and they do experience some steric interaction. This is also a gauche conformer. This is the same as that. They're, because of the symmetry of the molecule. And so I just calculated this for you a few minutes ago. 4, 4, and the whole thing was 19. So this is 4 and 4, 8 from 19 is 11. I just calculated that for you a minute ago. And so if you'll think about it, it is amazing how additive these interactions are. You know, was nothing that guaranteed that they had to be, but when chemists early on realized this, they were able to predict with amazing accuracy the heats of formation of some compounds and the energy barriers to some transformations. And so here this is a table that shows the different strains that we have just calculated. And so you may need to use these in calculating some of your homework problems. Now, cycloalkanes, remember I showed you this also in your molecular models. I showed you in particular cyclopropane, cyclobutane, cyclopentane, and cyclohexane. And so here they're drawn flat on the sheet of paper. I showed you how these molecules will distort some in order to avoid having a flat structure, because the flat structure just causes all sorts of energy increasing interactions. And so notice here, this is interesting. You don't need to memorize these numbers, but just note the trend. Cyclopropane has the highest heat of combustion per methylene. Methylene is a CH2 group. Methylene, per methylene. So this has the highest energy of combustion per methylene, then butane. And look here, now you get down to cyclopentane, it's much lower, and cyclohexane has the lowest of all. As you start increasing again, increasing the number of carbons in the ring, the heat of combustion per methylene starts increasing again. So it's just interesting. I would not say that you need to remember any of these numbers, but just remember this trend, the general trend. I showed you this earlier here, for cyclopropane. You've got the methylenes, the CH bonds of the different methylenes overlapping. You have the distortion of this should be an sp3 hybridized carbon. Notice how the orbitals are distorted away from 109 degrees. And so that's going to cause some angle strain. And also the CH2 eclipsing will have some strain there, torsional strain. So propane tries to pucker a little, but it tries to twist, but it really can't do much. Cyclopropane tries to distort a little, but it can't do much. Cyclobutane does pucker. It is not flat. And so the angle goes on down to 88. So this is an sp3 hybridized carbon. It should be 109. If this molecule were totally flat, it would be 90, which is a distortion and gives it severe angle strain. But it incurs additional angle strain in order to avoid having these eclipsing interactions between the CH3. So you relieve some torsional strain, but you incur, or the molecule incurs a little bit of extra angle strain by doing this puckering or bending. Cyclopentane, remember I told you this conformer is called the envelope conformation in order to avoid some of the eclipsing interactions between the methylene CH bonds. Not much angle strain either. Okay, so now we come to cyclohexane. Cyclohexane is going to be the one that you'll be spending the most time on. You'll want to read this quite a bit in your textbook and also look at the video that I made for you. So remember I showed you how it's possible to do a ring flip in which the carbon at one end, which is pointing down, is converted to pointing up at the other end. And so I showed you the ring flip. You'll want to make your model and manipulate it with your own hands so that you are able to do the ring flip and understand what's happening there. So you're not simply rotating the chair conformer around. You're actually doing a ring flip so that this carbon points up, that carbon points down. Okay? This carbon becomes that carbon, this carbon becomes that carbon. And so to do that, you go through different other conformers. So this is by far the lowest energy conformer, the chair conformation. And we will do a lot with the chair conformation. So you'll want to learn this. Then there's the half chair, in which the this is the highest energy of the conformers. And notice here you have symmetry. So the chair and chair, these are the same energy. This half chair is the same energy as that half chair. This twist boat, another conformer, is the same energy as that twist boat. And so notice this is the highest energy. The reason is because here, here, and here you have eclipsing of the methylenes, the CH2s. Here, here, and here are eclipsing. And so that makes the energy quite a bit higher. And so here you have, this is twisted a bit more, and so it becomes a conformation that is, halfway in between the half chair and the boat. It's called the twist boat, and it's the next lowest energy. And then the boat is one where a conformation in which you have C1 and C4 of this C6 cycloalkane, the cyclohexane. C1 and C4 are both pointing up. And so the problems with this that make this high in energy are, one, the methylenes here and here are eclipsing. The CH bonds of the methylenes here and here are eclipsing. The CH bonds of the methylenes back here and here are eclipsing. And so those will cause some torsional strength. This is a methylene and this is a methylene. And so if you draw in the CH bonds, here you have a CH bond that's pointing up and a little bit to the right. Here you have a CH bond that's pointing up and a little bit to the left. And so the CH bond coming off of these carbons at C1 and C4 are actually pointed toward each other a little bit. And so that causes some problems, some steric interaction that makes this go up in energy. You do need to memorize these names: chair, half chair, twist boat, boat. You need to know the structures that go with each one. You need to know the relative energies, not necessarily the exact numbers, but just that the chair is lowest, half chair is highest, that the boat is next highest, the boat and twist boat are in between, and the boat, look at it like this: the half chair and the boat are both at energy maxima on this energy diagram. The chair and the twist boat are both at energy minima on this energy diagram. You will need to know that. Energy minimum, energy minimum, energy maximum, energy maximum. So know which one of these is at the energy minimum, which one is at the energy maximum. You'll need to know the structures, the names. Okay, conformations of cyclohexane. Cyclohexane has no ring strain in a chair conformation. No angle strain. The angles are all 109.5. The carbon-carbon-carbon angles, the carbon-carbon-hydrogen angles, the hydrogen-carbon-hydrogen angles are all 109.5. You can make yourself a molecular model and look down the carbon-carbon bond like it's a Newman projection, and you will be able to see this. Okay, these are all in a staggered conformation, and so there is no angle strain and no torsional strain. So remember back there on that table, it showed that cyclohexane had the lowest heat of formation per methylene of all of the cyclohexanes, and this is why. This is why. This is important. you should learn this. Drawing the chair conformations, you'll want to draw this so that it has parallel lines, parallel lines, parallel lines. There's a lot more information than this given in your textbook. I think that the textbook is quite clear on this, and the textbook will help you. Notice that on each one of these, there's a hydrogen going up, axial position, axial position. The other carbon or the other substituent will be going out in the equatorial position. So on each carbon, you're going to have a substituent going up and out, or down and out. Each one of these is going to have an axial, each carbon is going to have an axial and an equatorial substituent. Right? Even if it's CH, it's going to have an axial and an equatorial, each one. So here you will have axial pointing up, up, up. Here you'll have your axial substituent pointing down, down, down. So it alternates as it goes around the ring. Down, up, down, up, down, up. And you saw that very vividly in the molecular model that I made for you and showed you in that other video. So here, this is axial and equatorial. You'll need to learn this. You need to become very comfortable with it. Okay. Yes. Monosubstituted cyclohexane. So this is where you start learning that substituents, and here I'm not talking about CH bonds. So substituents, something other than a CH bond, is going to be more stable in the equatorial position. If it's in the axial position, there will be interaction with this CH bond that's in the axial position and this CH bond that's in the axial position. And so those diaxial interactions, this methyl with the CH bond and the CH bond, increase the energy of the molecule. It's simple steric hindrance. And so it makes this conformation where the methyl is in the equatorial position will be more stable. Okay, and so here, if you have methyl, this molecule, the methyl cyclohexane, will spend 95% of its time in this conformation and 5% of its time in that conformation. The energy barrier is sufficient that this molecule just jumps back and forth across this energy barrier. So remember, you have double arrows here. This is showing an equilibrium. This is not a resonance structure. Okay, resonance structures, you have two structures, but those two structures actually represent the one structure of the molecule. It's not what's going on here. You actually have two separate, distinct structures, and the molecule is jumping back and forth between those two structures. So here, it's drawn very nicely for you, the methyl in the axial position interacting. And so this is at the 1 carbon, this is at the 3 carbon, and one of these will be axial and one will be equatorial. So this methyl is interacting with the one that's axial. The one that's equatorial is pointing away. And so here you can see at the C1, when you have a substituent, it overlaps with the CH bonds that are in the axial position at carbons 1 and 5. So this would be 1, 2, 3, 4, 5. So these are called 1-3 diaxial interactions because you start counting. 1, 2, 3, 1, 2, 3. So this is a 1-3 diaxial interaction, and that is a 1-3 diaxial interaction. Okay, let's see. So if you move the methyl so that it is in the equatorial position, you don't have 1,3-diaxial interactions. Here are the energy estimates of the 1,3-diaxial interactions. If it's a chloro substituent in the axial position, that's going to increase the energy by 2 kilojoules per mole relative to having the chloro substituent in the equatorial position. So let me say that again. Having the chloro substituent in the axial position increases the energy of the molecule 2 kilojoules relative to having the chloro substituent in the equatorial position. Okay, so this is the energy increase incurred by moving that substituent from equatorial to axial. Moving that substituent, any of these in this column, from equatorial to axial increases the energy of the molecule by this much. So if you'll think about it, chloro is just straight. It doesn't have anything. It's just one atom. But here, OH, that's 2 atoms. And so the hydrogen is going to be on there moving around like a propeller. And so its diaxial interactions doubles. So this is 2, that's 4.2. If you move OH from equatorial to axial, it costs 4.2 kilojoules. And then if you move CH3, if you move a methyl from equatorial to axial, it's 7.6. And as these substituents get larger, the amount of energy cost is greater. And as the amount of energy, here, think about that as the energy barrier. You're going to have an energy barrier to go up to this higher energy, okay? And so you're going to have to be going up to a higher energy. And so the amount of equatorial conformation relative to axial conformation is going to be here. If you have, if the axial is 2 kilojoules higher in energy, then the ratio is going to be 70-30. And as the energy difference between the axial and equatorial conformations increases, then the molecule will spend more and more and more of its time having the substituent equatorial rather than axial. Here, this is more about how you draw these. This is using the wedged bond notation. So chloro is coming out at you, methyl is going back. So methyl is going down, chloro is going up. Methyl is coming out at you, chloro is going out. So what they've done here is simply a ring flip. They simply did a ring flip. These two are exactly the same molecules. Okay, if you look at this, chloro is going up, methyl is going down. These are on opposite sides of the ring. And here, if you look at it, methyl is going down and chloro is still going up. These are on opposite sides of the ring. Okay, so these are the same molecule. It's just that they've done a ring flip. This carbon went up, this carbon went down. So anytime you do a ring flip, whatever is axial becomes equatorial. When you do a ring flip, whatever is axial becomes equatorial. And whatever is equatorial becomes axial. This talks about a different type of isomerism. So these are different isomers, here and here. Notice here the two methyls are on the same side of the ring. Here the two methyls are on opposite sides of the ring. Here the two methyls are on the same side of the ring. You have a hydrogen and a hydrogen. Here the two methyls are on opposite sides of the ring. Hydrogen and hydrogen. Okay, so this is the trans isomer. And here, notice this is saying this is the lowest energy conformation. Well, it's actually this one, where both of the methyls are equatorial. This one will be higher in energy, where both of the methyls are axial. Here you have one axial, one equatorial, one axial, one equatorial. These are going to be equal. And so this is called, these isomers, we're getting into stereoisomerism, where it's exactly the same molecule. The connectivity is the same. The functional groups are the same. The functional groups are between the same atoms. You have the same substituents at the same positions. It's just that the substituents are oriented in different directions in space. And so here you have the two methyls pointing up. Here one is going up and one is going down. If you have the two methyls on the same side of the ring or of the double bond, it's called cis. Cis, this is the cis isomer, okay? And notice it's italicized. And if you have the two methyls across, notice it's called trans, okay? And you can think of it as like Trans-American Highway or something like this, across America. Trans means across. And so that's what it means here. These are trans. They're across the ring. Here, cis just means next to each other. Okay, polycyclic systems. We're not going to cover polycyclic systems too much, but just look at it here as cis and trans decalin. Notice you've got the cis is in italics, trans is in italics. You have a dash between cis and the name, a dash between trans and the name. You can see the two hydrogens are both on the same side of the rings. Here you can see the two hydrogens are on opposite sides of the rings. This one's going up, this one's going down. Here, this one's going up, this one's going up, sort of. So, this is showing you cis and trans in polycyclic systems. And here, this is how you can draw it in larger, draw the substituent, the substituents in larger molecules. This hydrogen would be wedged up. This hydrogen would be wedged down. Okay. Here, the two hydrogens would both be wedged up. So, the cis isomers are almost always higher in energy than the trans isomers. And so, more on polycyclic systems. You're not, think of it as bicycloalkanes. A bicycloalkane, which we covered just a minute ago, similar to this, is a polycyclic system. We're not going to have that many polycyclic systems. I don't think that you'll ever be tested to know the name of this compound or know the name of that compound. On one of your homework problems, I guess there's a chance you might have to draw one of those, but other than that, I don't think you need to memorize these names. This one has been so important in chemistry, you will probably see it again. This is just sort of a favorite because of its historical significance. A lot of work was done to determine the reactivity of some functionalized bicycloheptanes. This norbornane is the common name for this. And books were written about this one molecule, functionalized norbornanes. And so remember the name. This is a heptane. 1, 2, 3, 4, 5, 6, 7. heptane, and it's bicyclo. And remember, you count the number of carbons in the bridges, 2, 2, 1. So here it is, bicyclo, 2, 2, 1, heptane. Notice the brackets, no hyphens. So that's the second time we've gone over that in this chapter. And so that concludes this chapter. And so I urge you to watch the video of my demonstrating the molecular models. I went to quite a bit of trouble to do that. I had to haul everything down to one of the rooms on campus and film it down there. I hope it benefits you, and you'll want your molecular models. You will want to make your molecular models, and anything that you don't understand from any of these lectures, you can make your molecular models, and that should help you, especially in working your problems. You know, it all comes together. You'll need all of it.